So the next lecture is about volume validation. And there is a saying in the field that the good thing about electron microscopy is that it always gives a volume. The bad thing about electron microscopy is that it always gives a volume. So you will have a volume, but you never know if this volume is the correct one or not. And I like to think of this problem as I want to have a good reconstruction, I need accurate data, I need to take good decisions at the level of image processing, and then I will have good reconstructions. Otherwise, if I have accurate data but I take bad decisions, I will have a bad reconstruction. If I have bad data, it doesn't matter what I do with the image processing, I will always have bad reconstructions. And so this GIGO is garbage in, garbage out, and this is something very typical in many systems. So if you don't put good data in and you don't take the good decisions, you will never have a correct structure. And this is a plot of the number of maps after this resolution revolution, and it is already a pretty old picture, so 2016. But now there are even more volumes, so this curve has continued to grow almost exponentially. And the point is that now this pressure to make good volumes is even harder because we have many more volumes reported. Okay, so I like also this picture that CryoEM is a very powerful tool, and image processing, the tools that you have there, they're also very powerful, but without control, so that is nothing. So you cannot leave them on their own, just hoping that the tools will do their best and always correctly. And there has been this bitter debate on what was the structure of the HIV envelope glycoproteins that you may be aware that this was 2013, I think. And it is not a criticism to this particular structure, but just to highlight what is the risk of not taking the appropriate measure to make sure that what you are publishing is really the correct structure. And here are some tools that you may use, and they are all, I would like to say, necessary conditions, in the sense that if your volume fails to fulfill this criteria, then that is throwing some suspicion on your volume. But if your volume succeeds in fulfilling all of them, still there is no absolute guarantee that your volume is absolutely correct. And these necessary conditions, they refer, we will see to each one of the individual items, but they refer to consistency with the data, consistency with between each other, and then there are some other validation tools that refer to resolution, to more consistency with the data, and there is an absolute validation in terms of the hand of the volume, and ultimately the comparison to an atomic model, if this is possible because you have high resolution, then that will give you the proof that your volume is correct. So the initial volume is crucial, is absolutely crucial. So if you start from a biased 3D volume, sometimes you are lucky and you are able to escape from that initial volume and go to the correct structure, but very often you are not lucky, and then you will end up with some 3D reconstruction that is totally incorrect. And normally this is seen because the FSC of your 3D reconstruction doesn't go very far, But when you look at the 2D classes, you see very fine detail in the images. So that means that there is good information in 3D in the images, but you have not been capable of incorporating it into the 3D. And in Sapien there are many different algorithms for initial volume. Even there are some of them that make consensus of initial volume so that you don't have to decide by yourself. But this is absolutely crucial. And this is one of the main mistakes of incorrect structures. And then all the rest could be seen as relatively minor mistakes that hinder a bit the resolution, but probably they are not the most important. This is really the most important. And for making sure that your structure is the good one, you can use you can reproject your structure and compare them to the 2D classes. So for instance, this is the reprojection, these are the 2D classes, and then these are the differences between those. And then what we shouldn't see any particular pattern in the difference, or at least the two images should look alike. And here there are some coefficients that tell you how similar those images are, and they should be as high as possible. And if you're interested in this protocol, this is in compare reprojections of Sapien. And here are the worst fitting particles. These are the best fitting particles, and these are the worst, and still the worst should be relatively good. Okay, so something else to look at is the angular distribution. So if your angular distribution is not ideally it should be uniformly distributed on the projection sphere, but this is ideal. In practice, you might have some areas that are overrepresented, and some algorithms are having trouble sometimes with these overrepresented areas, not always, but sometimes you see elongations along the overrepresented areas, and a number of reasons for that. One is attraction. So for instance, let's say that this area here with a little bit more projections, it starts gaining signal to noise ratio, and then all the particles around, they get attracted to that direction. And so this is a slight incorrection. It can be very severe sometimes, and it hinders completely the structural interpretation of the structure. But yeah, most of the algorithms, at least I would only trust those reconstructions that I have obtained with different methods and they are compatible with each other, because otherwise a single algorithm may have these problems of angular traction or whatever other problem in the angular distribution, and I cannot recognize because I don't have anything else to compare to. And there have been some ways or some proposals to put a number on how good the angular orientation distribution is. And this is CryoEM, I think it is the name of the program, and it is also incorporated in Sapien, so you can compute with there is a plugin CryoEM, and then you can compute for a particular angular distribution how good it is. So the closer it is to 1, the more uniform it is, and then the closer it is to 0, the less uniform and the more areas that you are missing you have. And something else that you can look at are the correlation histograms. So they all should look like a single population histogram. So sometimes you see two lobes, and these two lobes is a very good indicator that you have a mixture of two populations there. And you may see left tails, like in this case, that where even some projections, they have negative correlation to the volume, so these projections should be removed. You should be careful of removing everything below a threshold. So for instance, let's say you put a threshold of 0.15, and the reason is that the correlation depends on the defocus. So the stronger the defocus, the stronger the correlation. This is what we see here with this red line. And so 0.15 may be low correlation for highly defocused images, but it may be very good correlation for low defocus images. So if you systematically remove images according to their cross correlation, you may be systematically removing one of the low defocus, or not one, but the low defocus images. And you may also recognize a few outliers, and this is very useful to remove. So if you compute percentiles of cross correlation per defocus, then this is a very useful tool to get rid of bad data. And for that you may use high-res as gives this output. What is the cross correlation percentile within each one of the defocus groups? So you may use that to clean your data. And something else that you have to look at is the reproducibility. So this is no longer the case, but a few years ago, the data set was aligned to a single volume, then two independent, not two independent, but 3 reconstructions were performed out of this aligned data set, and then we were computing the FSC and repeating the process. But now the data set is split at the very beginning, and the alignments are performed independently. This is called the gold standard. So I don't claim that the gold standard is absolutely needed, but it is a useful way of making sure that the structure that you get on one of the sides of the processing is the same as the one that you get on the other branch, and this is a good indicator that you have the same structure twice with ideally 2 independent halves of the dataset. And something else that you should look at is that there is no overfitting. So overfitting was commented, well, it is a very well-known effect in the field. And the thing is that sometimes you see artifacts that are that do not belong to your structure. So that is overfitting. Actually is a model, not model bias, but map bias, if you want. So there is a ground truth, and my object is the ground truth plus something else. So this something else is the bias. And for instance, a very typical sign of overfitting are these stripes around. So these stripes outside your structure means that you have some problem with the angular alignment typically. Some other very common indicator that you have a problem is this negative halo around your structure. So that is a problem with the CTF normally. So you have not estimated or corrected the CTF correctly. And some other idea, this was by Bernard Heyman, is that the 3D reconstructions that you get with your data should be better than the ones that you get with noise. And let's see these examples. So they are very illustrative. So let's say that I make a 3D reconstruction with very few particles. Then my resolution as measured by the FSC will be low. Then I add more particles, I have a little bit better resolution, and the more particles I add, the better my resolution is. But then, if I do the same with noise particles, so there is absolutely no signal in these images, but I take noise images, I align them with respect to reference, and then I make a 3D reconstruction. The more noise particles I add, also the resolution is improving. So this is a very surprising effect, and it is an effect that you may not expect and that you may have in your data. So if you have empty particles in your data set, the more empty particles you add, the better the Fourier shell correlation will be. But simply because these noisy particles help somehow to align with respect to the reference, but it is not because you are having a better structure, but you are making a systematic error in both halves, and then the systematic error is rewarded by the Fourier shell correlation that only compares the two volumes to see if they are equal. So at some point, these two curves, they for data in which you have a significant fraction of noise particles, these two curves overlap, while in a good 3D reconstruction, these two curves should never overlap. So the noise resolution should be always above the particles resolution. Something else is homogeneity. So all these tools, they are designed to work with a single homogeneous population of particles. But very often we have a mixture of our particles in different conformations, or even broken particles, or contaminations, or incorrectly chosen particles, or whatever flavor of incorrections that we might find. So for doing this distinction between different structures, we use 3D reconstruction, 3D classification, and this 3D classification will identify homogeneous populations, and this is good, and we are all familiar with these schemes. But we should be aware that 3D classification is a very unstable process. So if you run it once, you get something. So a particular image is assigned to this class. If you run it twice, or a second time, that same image is now assigned to a different class. So that means the estimation of what is the class membership of that image is a parameter estimation, and there is so much noise that this parameter estimation is very, very noisy. And for some images it is clear, for some other images they are not so clear. So you should always repeat this 3D classification process a few times, just to make sure that the images that you are putting together, they are always together, so that you can trust the decision of putting them together. Then there are these ideas about resolution. Resolution is something that we measure normally through the Fourier shell correlation. So the Fourier shell correlation compares what is the correlation of bandpass filtered versions of the two reconstructions that we do from the two halves of the data set. So if they correlate very well, then you trust your volume, but actually you trust your process, or not trust your process. So the thing is that if you make systematic errors, these errors are made twice in each one of the halves, and they correlate a lot. So if there is no correlation, then you don't trust the structure. So that is why we use the FSC, because if it is low, then we cannot trust it. But if it is high, still there is this possibility that you are committing systematic errors in both halves. And resolution is something that we measure with FSC in a global way, but it can also be measured locally. And actually, a few years ago, well, many years ago, 15 years ago, we computed this, we suggested a way to compute the spectral signal-to-noise ratio in any direction. So that means Fourier correlation and signal-to-noise ratio, they're very much related quantities. The specific relation may not be analytical. The analytical relationship that we normally find is comes only after a lot of simplifications, but they are related. And if they are related, that means that if we have, for instance, an uneven distribution of angles, then we have, let's say, more top views from a particular structure. So in the corresponding plane in the 3D Fourier space, we should have a better signal-to-noise ratio because we have measured those coefficients more often, and then we can compute better averages. So this is what the spectral signal-to-noise ratio is trying to capture, and the Fourier shell correlation can be thought of as a radial average of this spectral signal-to-noise ratio. Radial average in a very loose sense. So it is a curve that is radial and that somehow is related to the signal-to-noise ratio. But in the last years, we have, as a field, already acknowledged that the resolution is not something global, but it is also something local. If there is, for instance, a part of the molecule that is moving, then we will have less resolution in that area. And there have been many successful algorithms like ResMap or MonoRes or DeepRes or whatever. But the point is that the resolution is not just a value, but it is a value that depends on the direction, as we have seen with the signal-to-noise ratio, and also depends on the location. And actually the number given by the Fourier shell correlation, especially this 0.14 threshold, seems to be the resolution of the best voxel in the best resolution of the best voxel. So in the local resolution map. So the Fourier shell correlation for this map probably would be something like 4.5. So but this what this local resolution is saying, this best resolution is obtained at some point, but not all the map necessarily has the same resolution. Something else that we can look at to make sure that we have a correct structure is the B factor. So the B factor is how the coefficients decay in the Fourier space. And this is again a radial average, but it gives you already an idea that correct structures should decay in the Fourier space. And this is a property of natural objects. And if you have a structure that whose B factor goes up, then that is a bad indicator. And actually, proteins have a relative range of B factors, and I don't want to give a range, specific range written in stone, but it is somewhere between 150 angstroms and, let's say, 20 angstroms squared. So if your volume doesn't have a B factor in that range, then that probably is not the correct 3D reconstruction. So there are some problems in the Fourier weighting or something. Something else that you can look at is the alignability. Alignability means when you are aligning your projections with respect to a volume, you have to decide which is the best orientation for each one of the projections. But you may wonder where is the second best, the third best, and so on. If they're all clustered around the best orientation, then probably you trust that that is the orientation of that particle. If those are all scattered, then you don't trust, you're not so sure where that particle is coming from. And we can put a number onto that certainty, and this is what we published in 2016. And that number, if that number is above 1, then you can be pretty sure about your structure, about the orientability, alignability of that particle. And if that number is below 1, then you're not so sure. And for instance, here we have the comparison between these two HIV glycoprotein structures, and we see that for one of them the alignability of the particles is pretty good, while for the other one the alignability of the particles is not so good. So that means that we have a tool to make sure that the structure that we have allows the alignment of the particles. And then we already mentioned this Fourier cell correlation and spectral signal to noise ratio, so those are related quantities. The specific relation is unknown, at least in analytical terms, unless you make a lot of simplifications, but yeah, but they are related quantities. And then there is this technique that allows you to verify what is the handedness of your structure. So from the image processing point of view, we can take all the images and compute a volume, or we may take the mirror of all these images and compute a mirrored volume. And from the structural consistency, the volume is consistent with the images, only that they have been flipped. So these flipped images are obtained by putting the projection in the opposite direction from the correct one. So there is no way from the image processing that we can tell which one of the two, the mirror or the unmirrored structure, is the correct one. And then Richard Henderson came out with this idea that you can tilt your specimen. So you take two images, one that is tilted, another one that is untilted, and the tilt here doesn't need to be very strong, so just 10-15 angstroms, and then you make the angular assignment of both. And because you know what was the experimental tilt, you can compare those two angular assignments, and for the correct hand of the 3D reconstruction, the relationship between the two angular assignments should be the tilt that you put into the microscope. So this is a good way, a very good way of checking what is the handedness of the 3D reconstruction. And there is a server that at the VI where you can submit your data and then see whether you have the correct hand or not. And otherwise, so we have seen tools that can be applied directly on the volume or the volume and the images, and then if you have a good structure, then you should be able to see it, or if you have enough resolution, an atomic model should tell you whether your structure is compatible with the atomic model. And if you have many mismatches between the atomic model and the CryoEM structure, and this is ultimately the correct, the final proof of the correctness of your structure. And there is also an interesting idea, that is that when you make an atomic model of a cryo-EM structure, of a cryo-EM map, it might be that there are regions for which you are very sure that the atomic model goes in that way, but there are some other regions, especially because you have lower resolution there, for which you have more space to, or more possibilities to fit your atomic model. So that means that you're not so sure any longer about the correct position of the atomic model in that area. And that uncertainty is also another way to validate your volume. So if the areas for which you don't have such an ambiguity, those are good areas. The areas where many different atomic models could be fitted, those are less resolved areas. And there are also a very nice paper, but relatively recent, couple of years ago, where they make a lot of comparisons of different measures about the similarity between a map and an atomic model. So there are many different things that you can look at to make sure that the atomic model is supported by the cryo-EM. And here is another one. This is MapQ. MapQ is comparing how visible your different atoms are in the 3D structure. And yeah, in general, and there are a couple of methods more, like the directional resolution. Directional, you have monodir, that would be an extension of this monores and all these local resolution tools, but now incorporating the idea that the resolution is directional. And also we have recently published FSEQ that somehow is complements this idea of MapQ. But in general, I would like to convey this idea that once you have a structure, you should make all the you should take all the worries to make sure that what you have is really the structure that you are interested in, because otherwise you might end up into local minima, and these local minima they spoil your structural information. So this would be